objectives of the smart sustainable home, which are to improve sustainability, such as reduce CO2, improve the quality of life of your family, and finally save money. We also introduced the concept of the smart home grid, a system that will intelligently manage energy in your home to fulfill those three objectives. Now, in case you missed those, you will find a link to those videos here, and I will also add a link to those videos in the description. Whilst not technically advanced, today's video will be an intermediate level, introducing how to build your own intelligent sustainable home orchestration should off-the-shelf solutions fail to meet your requirements. We will first revisit in greater details what a smart home grid is and why you need it. Then we will look at a DIY approach, do it yourself, and why they usually are a bad idea except for very specific use cases. We will introduce the Home Assistant and the Node-RED combo, which we will use as a foundation for the smart home grid. And finally, we will provide an overview of test-driven development, for which we will describe a simple yet practical example of smart lighting. This brings us to the concept of the smart home grid, a system that will intelligently prioritize and route energy to the systems that most need it to fulfill the three objectives of the smart sustainable home. The diagram below shows the architectural view of the system we are proposing in this channel and introduced in earlier videos. By architecture, we mean the high-level view of the system that we will build step by step in the advanced videos of this channel. Those smart services would, for example, automatically activate or pause the car charging service depending on the production of solar panels, or increase shading to reduce cooling costs. As we can see, the entire purpose of the smart home grid is to provide smart services to the home. Now, before we proceed, let's have a look at the service which is not smart. Irrigation of my garden is triggered daily at the same time. As you can see, watering the garden on that day simply was not very smart, resulting in a waste of natural resource, water in this case, a waste of money, the cost of water and electricity to pump the water. There got to be a better way. And this is precisely what a smart home grid will achieve. The smart home grid orchestration system must be able to receive telemetry from various sources such as weather forecast, sensors, solar panel statistics, and many others to make the right energy-related decisions without you having to intervene. In the case we just showed, if it's raining, just skip watering the garden today. This intermediate level video is all about practical details for implementation. At the end of this video, you will understand how to build your own smart home grid orchestration system, and we will provide an example of smart lighting and solar routing implementation in a simple lab environment, implementing the elements shown in green in this diagram. Let's get started. Energy consumption means starting or stopping a charge, for example, initiating or pausing charging your electric vehicle. Triggering any of those two actions must be possible without you having to touch the car charger itself. This must be true for all other electric switches such as heating, cooling, lights, irrigation, and many others. In other words, all electric switches and all sensors must be connected, and it must be possible to trigger any of those remotely. All those connected sensors, electric switches, and others are often referred to as connected things. They are often referred to as smart if they can be controlled from a remote location. The most typical setup for connected things is cloud managed. Almost all smart connected electric switches vendors are in this category. In this example, when you install, for example, a car charger, during the installation you will be asked to provide access to the internet, typically through Wi-Fi. And once connected to the internet, the car charger will register with the vendor servers over the internet. And the user will leverage the mobile application of the vendor to control the equipment. Now, in reality, the application will just reach out to the vendor servers over the internet, and from there, the car charge can be remotely activated. The key advantage is, of course, ease of use. You just plug your new electric switch in add your Wi-Fi network settings, credentials, and voila, it works. The obvious disadvantage is that this setup only works when you have internet access. And the second disadvantage, which is actually the bigger one, is the multiplication of applications on your smartphone that do not talk to each other. It is very common to have over 5 applications to control or have visibility on equipment from 5 different vendors. Now, there are more advanced cloud managed solutions, but we'll keep this for future videos. The other option is to have all your devices centrally managed on premise. In this model, you would have a controller in your house that would orchestrate all your devices, such as Home Assistant, highlighted here. This would include receiving telemetry from your home devices and online services, as well as activating or stopping them. The major disadvantage, of course, is that you must add a server in your home and maintain it. There are, however, plenty of advantages. So yes, automations will still work whilst your internet connection is down, but this is a minor point. The main advantage is that as you centralize all informations and decisions in a central location, and you can orchestrate all your devices from this single central point, which will become the brain of your home. The final concept I would like to talk about before we proceed are any communication protocols. Whether you're using a cloud or locally managed system, the controller must communicate with the devices. They must talk a common language. This language will be referred to as communication protocols. REST APIs, Modbus, and MQTT are examples of widely used communication protocols. Now, to get started, you do not need to know much about them, except that they should be regarded as communication languages. For two people to communicate together, they must be able to talk at least one common language. The same goes for the connected things. If a device only talks Modbus, you need to ensure your controller does speak Modbus as well. Whether it is on the internet or locally doesn't really matter much. So here comes the $1 million question. Where do I start to implement my smart home? One extreme, described at the bottom, is the option of not doing anything and just leverage existing applications. Well, whilst this is very easy to achieve, it also results into many limitations, as those mobile applications do not talk to each other. We will review concrete cases impossible to achieve with this approach. The other extreme is to leverage your programming skills, your software development skills, and build your own system. This is labeled as the other extreme at the top, do-it-yourself, abbreviated DIY, or fully custom. Now, whilst the option of just leveraging existing applications is easy to understand, let's review what fully custom really means, implies, and why I believe going into this direction is usually a bad idea. Let's take a very simple example. Without any application or any local controller, I would like to interact and control a connected thing. Well, in this example, I will use my laptop to communicate locally with my Victron energy charger and get some statistics from it. I first looked up the specifications of my solar charger and found it can communicate through Modbus. Looking up the Victron website, I also found a documentation that provides all parameters to be used when interacting with the charger. Whilst I could theoretically leverage any programming language to achieve this, I will use Python, given the vast number of libraries available, which will help me save time.
So let's get practical. We're now looking at my home photovoltaic system statistics from the Victron Energy website. The information I would like to retrieve is 69%, which is the current level of the battery. There is we're at night at 7:52 p.m., so there is no production of sun, and my house is consuming quite a bit with over 1,000 watts. The question is, how do I get a Python code to retrieve 69%, which is this value, without having to go over the internet? First option, I can Google it and type a question such as Python code to get state of charge of a battery Modbus Victron Energy. And this will most likely give me access to previous good examples where previous people in, for example, the Victron community had to do the same. So they really went ahead and provided information such as what are the right libraries and what is the right code to get this done. So now, in all honesty, if I use it as is with my kit, it will not work. A more modern approach than doing a web search is to use generative AI. So you're leveraging ChatGPT. I can type a question such as, please generate me a Python code that will retrieve the state of charge percentage level over a Modbus from my Victron energy charger. This is clearly a step ahead because first it will tell me which library I need, and it will also tell me how to install it, which is this pip install PyModBus in case I have not installed it. It's going to be produce a very clean and simple code which I could use. It will not do a great job at retrieving the specific settings which I have to figure out myself in this case. And finally, it's going to give me a fairly high level code, so I would still need to customize it. After a bit of fun, I have generated this code which has the current argument and correct parameters. So the state of charge is parameter 266 according to the Victron Energy Modbus TCP documentation. Therefore, if I run this code, it will tell me that at 7:54 that the current state of charge is now 68%. And if I go back to the web interface, this is now correct.
Now, let's look at why it typically is a bad idea to go custom. Well, first and foremost, getting 10 lines of script to work as a proof of concept is great. Adding more and more functionalities will increase the effort exponentially. For every functionality you will add, you will have to maintain it and must think through dependencies, race conditions, databases, data modeling, and many other things. If you do not make a living out of it and therefore are willing to spend time on it, do not start custom. The next reason is even more obvious. Other smart people have already done the hard work for you. It is always wiser to leverage existing work than to try to reinvent the wheel. And finally, the most important reason, it's not secure. Let's think through what functionalities we need to orchestrate at home. We need to communicate with an existing set of APIs on the local network and often open it to the internet. We need to set up a SQL database and store telemetry data on it. To do so, you will need to manage various sets of credentials. And if you check the top 10 application security risks from the Open Worldwide Application Security Project, also known as OWASP, you will see that database SQL injection, broken access control, insufficient data input validation are the most common reasons for being hacked. I will add a link in the description if you want to know more, but cybersecurity alone is a sufficiently good reason to never go custom without leveraging secure libraries. Bottom line, unless if your code delivers only one functionality, is a closed system not connected to the internet, coding your own system is always a bad idea. So in the end, if leveraging many siloed existing vendors' applications lacks flexibility and if going custom is a bad idea, well, what should you do? My recommendation is to use an existing controller, whether it is cloud or locally based, and leverage a low-code, no-code tooling. This approach combines the best of both worlds, leveraging an intuitive web interface you can add smart functionalities with, little to no programming skills, and achieve the same level of automation than a fully custom code. There are various ways to achieve this, but we will focus on the combo I recommend: Home Assistant with the Node-RED add-on.
So let's review a practical example. I have set up a small lab where I've hooked my IKEA lamp onto a Shelly Pro 1 p.m. electric switch. I've used this switch because it will show me the electric usage over time. The objective of the lab is to ensure that the lamp is only lit when there is enough green energy available to power the lamp. If I go to the Shelly website, which is where I am right now, the Shelly Control Cloud website, I have access to this lamp and I can turn it on. It's a cloud connected and managed device. After a few seconds, it will stabilize in between 3.5 and 4 watts. So let's say 4 watts is what this lamp needs to continuously run. Let me turn it off. If I look at the Victron website, which shows the real-time information on photovoltaic energy production, I can see that we're at night, it's over 8 p.m., and there is 0 watts being produced. So in my lab, ideally, the lamp should be turned off immediately. In order to do this, I would need to get both solar energy information and the Shelly information for my smart switch on the same interface. And this is where Home Assistant comes to play. Home Assistant is a free software which can be downloaded. Just Google Home Assistant and you will have access to it to do exactly this, to be the brain of your home um, domotics equipment and energy systems. I will not introduce how to install Home Assistant, its integrations, its add-ons. There are millions of excellent tutorials on how to get this done. I will put a few links in the description. Now, I've already integrated a Modbus integration for my Victron systems, so I have access to the production, which is currently zero production of photovoltaic energy, and I'm still consuming over 1,000 watts. My diesel generator is not working, and my batteries are at 64% now. At the same time, I have access to other informations from my car, from my heating systems, as well as to the famous lamp, which I just talked about. I also integrated this Shelly lamp, so if I click on Shelly lamp, I will switch it on, and after a few seconds, it will stabilize at 3.8 watts, as we can see. Let's say 4 watts to make it things simple. If I go back to the Shelly Control website, I will see exactly the same because both the Shelly Control and Home Assistant are connected to the lamp. And so we have now one system, which is Home Assistant, where all the devices will be visible and all telemetry will be received. Finally, it's important, if not vital, to get access to those informations, be able to activate, deactivate them from wherever you are in the world. I recommend for anyone going to Home Assistant to get a Home Assistant cloud subscription from Nabukasa. It's paid for a very fair price subscription. However, all of the money goes to the developers of Home Assistant. And this is what keeps the software running and keeping so good.
Now that our setup is complete, let's review test-driven development, which is a functionality development process relying on defining test cases before developing the code. If you're not familiar with software development or testing processes, do not worry, we will take it step by step. In today's example, we want our lamp to only be on when there is excess green energy to power it. In test-driven development, we must first define the test and then run the test, which will initially fail, and then only create the code for the test to pass, and finally refactor and improve the code. At first glance, you might wonder, why on earth would I waste time running a test which I know will fail before writing the code? Well, in reality, this is a very simple yet very effective way to force you to think through what success would really mean.
So let's think through exactly what test would demonstrate that my lamp only runs on green energy. As we can see, the lamp currently consumes a bit more than 4 watts, but whatever, let's say 4 watts is just peanuts at the end of the day. 1000 plus is the current demand in electricity from my home, and PV charges is photovoltaic generation, which is currently zero because we're at night at 8:34 today. What I would really need is, in case the value from photovoltaic charger generation minus the load still has 4 watts available. So for example, if it was 2000 watts generated minus 1000 load from the house, I still have more than 4 watts available, and therefore I could trigger the lamp. Currently, as there is no generation of electricity from green energy, I just get it only in my case from my batteries, but it would be for most of you from the grid. The lamp should be turned off immediately because there is no green energy currently available as we speak. This is where we would like to introduce Node-RED. So I've already clicked on Node-RED, and I'm using this very basic setup to show you what it does. I will not introduce how to install Node-RED and any introduction to Node-RED. I will put some more links to it. This is the basic inject node, nothing special. I just renamed it. And this allows me to turn the lamp on. And if I click on this call service node for Home Assistant, the only thing it really does is that it's a switch. It's going to turn the Shelly switch on or off. And I just had to select the right device, the right functionality of this device, which is switches on and off, and that's roughly it. So if I look at the same from the second node, which is the turn off, I pretty well have exactly the same, except I'm going to be turning off the switch. So here I can click here and turn off the lamp. If I go back to Shelly control, indeed, it turned off everything. If I go back here, I can click the lamp on. It was called again, and if I go here, it's using roughly 5 watts.
Now that we have a good grip on what success would mean, i.e. what test case must be passed, let's tackle the creation of the code. As a reminder, we want to make sure we only keep the lamp lit through excess green energy. More precisely, if we have at least 4 watts of green electricity produced at any point of time. Well, now that we understood the test case, the code to produce is rather simple and straightforward. We just need to retrieve the current solar production and electricity consumption of the house. After subtracting the house consumption from the solar production, if we have 4 watts or more available, we turn the lamp on, else we turn the lamp off. The process will be repeated regularly to turn the lamp on or off 24/7. Please pause the video if you need to review the logic described in this flowchart. Else, let's see how we can program this in Node-RED.
Here is the code that will implement the workflow we just did show on the slide a few seconds ago. It's currently not in operations. I did not connect the inject node to getting the statistics. We'll do that in a sec. The inject node is about the same we had previously, except that this time I'm going to automatically inject after 1 second after operation, and I want it to repeat the injection every minute. So it's going to be triggering the workflow every minute. Then I will retrieve the solar production and house consumption and store those values into respective variables, which are just storage entities, which will be flow.victron PV charge and the consumption, which is the total AC load of the house. And from there on, it's extremely easy. Is there enough green electricity available? I just need to take the amount of electricity produced from green energy minus the load, and I have to ask myself, does it give more than 4 watts, which is what I need for my lamp, or less than 4 watts? Very simple and straightforward. My lamp is still on and is currently consuming 5 watts, by the way. I'm therefore going to be activating this code by connecting this. Now it's fully functional. I'm going to deploying it. The deployment always takes roughly 5 seconds. This is where the immediate action may generate a small error when you first wait for it, but if we wait 1 minute, it will work. But let's not wait 1 minute doing nothing. I'm going to inject it again. And as we can see, it got 0 at 8:43 in terms of solar production. It got over 1,000 from house consumption. And therefore, the logic is there is less than 4 watts available of green energy, and therefore it called the turn off switch available at 8:43 as well. In this case, the code is successful. It did turn off the lamp because there was no green energy available. The final step in a test-driven development cycle is to refactor/improve the code. And when you think about it, there's a big flow that in this code, which is that the code is running every minute. We're at night and we're in the winter. So for the next 13 to 14 hours, it's going to be triggering the entire algorithm and starting to get all of these questions and reach out to the lamps pretty well every minute. So it's going to be turning off the lamp every minute, non-stop for the next 14 hours. Question is, why on earth would I do that? It's going to be much better to only do this during the day when there is sun. For this one, I'm going to be using a different node instead of an inject node. I'm going to use Big Timer. Big Timer is a very advanced node that, if I double click on it, will give me a lot of options. Of course, dawn, dusk, sunset, sunrise is different depending on where you live. So you need to put your latitudes and longitudes. It's very easy to do, by the way. You just go to Google Map and you go more or less wherever you live, and you right click, and that's going to give you those two values, 34 dot something and minus 118 dot something. And those are the values that you will want to plug into the latitude and longitudes. Small hint from experience, you just use sunrise off at sunset, and I recommend a small offset of 60 minutes. So only start 60 minutes after sunrise and stop 60 minutes, or just leave it like this would be even better, actually. Now, I've already done this myself for my home. I'm going to disconnect this temporarily. I'm going to look into this version, and we will look at what it does. I've already done this for my latitude and longitude, and therefore I can see that this is off for the next 12 hours. If the condition is successful, which is the case, it's going to be outputting every minute either a 1 or a 0. And in this case, if it's a 1, I will want to continue. If it's a 0, it means that the condition is failing, and therefore it is part of the PC which is off. So in this case, I'm going to be deploying it as is, and this is going to be my new code, but it will only be triggered 60 minutes after sunrise, which is going to be way smarter and will not trigger unnecessary calls to all of the lamps.
In today's video, we have reviewed how a smart home grid orchestrator could be created using Assistant and its Node-RED add-on. We have reviewed an implementation of solar routing where excess solar energy is used to power a lamp in a simplistic lab environment. The lamp only needed 4 watts. However, if you configure 2500 watts, you would power a boiler with excess green energy, or 3600 watts, and you would start charging your electric car with your excess green energy as well. In both examples though, work with an electrician to ensure your setup supports such loads and that your electric switches will not introduce any safety risk. Electric car charging can be done in an even smarter way, which we will review in detail in an upcoming video. I will even dedicate 2 full videos on how you can charge your electric car, since in my experience this is where most of the savings can be achieved easily. As always, if you like the video, please give it a thumbs up. And if you want to see more ways for you to become more sustainable and save more money, consider subscribing to this channel. Now it's your turn. What key smart sustainable services have you been able to implement in your home? How did you implement them, and how much savings have you been able to get out of it? Please share your experiences in the comments below. Thank you for listening to this video. I will see you in the next one.